In this video, we are going to study the Spinlock, which is implemented in this courses repository, and the Rayon's parallel iterator, which is the parallelism library built on top of other concurrency libraries. So in most cases, people want to use parallelism library because it abstracts out all the concurrency details into libraries. And I will show you how easy it is to use the Rayon's parallel iterator. Okay, first things first. Let me first introduce Spinlock, which is in this repository, the course repository, and you can search for the lock folder and source folder and then spinlock.rs. It defines the Spinlock, which is trying to acquire a lock in a spin loop. So that's the reason why it is called a Spinlock. Okay, Spinlock is just a Boolean, but it is the Boolean can be accessed by multiple threads. That is the only difference from the usual Boolean to the Spinlock's Boolean, atomic Boolean. It is a Boolean, and that Boolean signifies whether the lock is held or not. So if it is true, then it is held by someone. It is false, then it is not held by anyone. So it's the meaning of the Boolean inside this Spinlock. And this default trait is the trait for the default value of a Spinlock. And in this case, it is false because at the beginning of an execution, a Spinlock is not held by anyone. That's the reason why it is given false. You can see if you already read the book about Rust, then you can immediately see the syntactic components of this few lines. This is the default trait, which is defined in the standard library, which designates the default value of type. And this is a function that returns the default value. And self in this context is the same with the Spinlock here. Self is for referencing its own type. It is creating a value of Spinlock, and the inner value becomes false in this case. So far so good. And in this block of code, we are going to define the lock operations of a Spinlock. So here a lock function is given, and here a type token should be provided for regarding the Spinlock as a lock. Token is basically a value that is returned by a lock function. Lock function not only acquires the lock, but returns some receipt or proof that, oh, this lock is held by you. The token serves as the role. So for Spinlock, it is just the unit value, which doesn't have any meaningful information. But for other kinds of locks, they will have other kinds of more complicated tokens. So in this case, for Spinlock, you can safely ignore the contents of this token. So let's just ignore that, and let's look at the lock and unlock functions. In lock functions, we are going to define what is called backoff. And backoff is basically a data structure that makes our lives easier to deal with a spin loop. In spin loop, it is discouraged to spin as fast as possible, because when some conditions are not met, or in particular the lock has not been acquired, then it is likely that for a short period of time you're not going to acquire the lock again. So if you didn't acquire a lock, it's beneficial to just wait for a few moments. It will not be seconds, but it can be some milliseconds or microseconds. And this backoff is exactly doing that. When backoff snooze is called, it is just waiting for a few minutes, few moments. So it is also exponentially increasing the latency. At the beginning, it is probably immediately returned in the hope that the lock is just temporarily held by others. But if you try it again and again and again, and you call snooze multiple times, then it says that, oh, I'm not going to acquire the lock soon. So that's the reason why I'm going to wait a little bit more, possibly yielding to other threads the turn. Okay, so this is the mechanism for exponentially backoff in the spin loop, and this is the spin loop. And here it is trying to atomically swap a false value into true. The precise meaning of all the things will be discussed in the later, but at this stage, just memorize that lock is trying to atomically replace a false value into true. And if it is successful, it is going to return. So it is very much okay because this function atomically replaces false into true. That means that the lock is held by someone, and that someone is me. I just replaced it atomically. A lock function is very much similar. It is just trying to store the false value into the store. So the meaning is that, oh, I finished accessing the internal data, and so I release the lock by storing the false value into the inner value. So effectively, this will signify the other threads that the lock is from now on released by me, so it can be acquired by you. This function is marked as unsafe because this function signature not always guarantees the safe uses of API. For example, you should not unlock a spin lock that is not held by, not acquired by me. Also, you have to give the token that is the same with the token that is returned by this lock function. It is not guaranteed by the Rust API. This is the guarantee that you should satisfy. That's the reason why it is marked as unsafe. The implementation is not 100% guaranteed to be safe because it has a contract that the user of this API should satisfy, and namely the token given by this lock function should be given to the argument here as a token. And yeah, this is basically the meaning of this unsafe. And there is other functions that is going to try to acquire a lock instead of spin looping here. But it is almost the same as above, so I will not explain it in details in this course. The implementation of this, what is the meaning of the compare and swap, and what is the meaning of this acquire, release, will be discussed in later videos. Okay, so far so good. We studied the APIs of the Spinlock and the reason why this should be marked as unsafe. And now I'm going to explain a higher level API of Spinlock that removes the necessity of using unsafe marker here. So this is the higher level API. So it defines the trait for which rows locks should satisfy. So here we are going to define a token type lock function, which is returning token as I explained, and the lock function. And as I explained, the lock functions is marked as unsafe here, and it is safe only if it is called with a token given by the corresponding lock function. So it is described in here. It is not guaranteed by Rust, but it is documented here, and the user is expected to satisfy the safety condition. Okay, so far so good, and we are going to explain the higher level API's benefits. So recall that in the previous lecture we discussed that lock has to satisfy two guarantees. The first one is that the lock and unlock should be matched, which is represented as here that the token that is returned by lock function should be given to unlock function, and it should be matched. So that is represented in this API's safety guarantee documentation. And the other part of the guarantee that user should satisfy is that the data that is protected by the Spinlock should be associated with the lock that is protecting it. And these two aspects are dealt with in this higher level API, and these two aspects of guarantees or contracts are automatically satisfied when using this higher level API. So let me explain the struct here, which is consisting of lock and data. As I explained, the lock and data should be paired. They are the two sides of a single coin, so we need to put them into a single struct. Here I put an unsafe cell. Here I wrapped a T with this unsafe cell, and which means that it has an interior mutability. This is very much okay because it is actually having interior mutability. When using a lock, you're going to mutably access the inner data using only shared references. That's the reason why we need to put this T into unsafe cell, which signifies that it is interior mutable data. So it is only for Rust. In Rust, when you are going to define an interior mutability, you're going to put the data into this unsafe cell. So just memorize it for now, but if you are interested in the technical details, please search for unsafe cell interior mutability in Google. This is the obligatory lines for marking the lock type as send or sync. So the types T, the underlying type T, should be sendable because it is accessed by multiple threads. So it is at one time accessed by thread A, and then it is sent to thread B, which acquires the lock at the next time, and it is going to access by C, therefore it should be sent to C as well, blah blah. So T should be sendable. However, there is no need for T to be sync, which means that there is no such a case that multiple threads are accessing the data T at the same time. It is guaranteed by the implementation of the Spinlock or other locks. So in Spinlock, when a thread acquires a lock, then it is the only thread that has acquired the lock, so there is no way T can be accessed by the other threads. That's the reason why it doesn't need to be sync. There is no concurrent accesses at the same time to the same data of T. Furthermore, they are marked as unsafe because the guarantees, just as I said, are guaranteed by the implementation of lock. It is not guaranteed by automatically guaranteed by the Rust type system. It is guaranteed by our own implementation that should be manually inspected. That's the reason why this line should be marked as unsafe. That signifies the fact that, I need to manually inspect that lock types are actually send and sync. Okay, so far so good. And we are going to show the internal implementations of the locks. When you create a lock using a row lock type, for example, a spin lock, using a data type T, then you're going to be given a data of type T, which is the initial value to be protected inside this lock. And the lock will be the default value. For Spinlock, it should be the false. And furthermore, the data is also initialized. It is unsafe cell, and it is be given data. Okay, and you can destroy the lock and get the data, inner data T. This is the API that does that. When you are given the total ownership of this lock, then you can just destroy the lock and then get the inner data. So it is no longer protected by the spin lock or other kinds of locks. So it is the API for that. And this is one of the most interesting API of this lock types. So when you call a lock, it not only acquires the inner lock, so that you get the token, you are going to return the lock guard. Lock guard, as we discussed in the previous lecture, is a proof that you has acquired a lock. And as a result, you put the lock itself, and then you're going to put the token here. Token is returned by the lock, and it partly proves that you have acquired a lock. So, and it should be given to the unlock function, so that should be remembered inside this lock guard. So far so good. And this is the type that is guarantees or proves that the lock has been acquired. And how can we use it? So in the in the lock guard type, it has a scope that is statically guaranteed to enclose the lifetime of this lock guard. So recall from the Rust book that when the scope is used at this point, then this struct is guaranteed to not outlive the scope that is given as. The lock guard should be dropped before the lifetime S has ended. So that's the meaning of this scope. And this scope is here because you acquire the lock using a lifetime. So this is the lifetime of the lock, and it is immutably borrowed here. And this scope here, the scope of this lock, is just copy and paste it into this lock guard here. It is elided, but it is still guaranteed that this lock guard does not outlive the lifetime of the lock here. It is very much expected because lock guard should not outlive the lock itself. So it is guaranteed by the lifetime that is described here and here. Okay, so far so good. And the lock guard also has a reference to the lock. So it is basically the reason why this S is here in the implementation of this lock guard. And you also have a token that should be given to the unlock function. So there are many functions here, but the most interesting part of the line is this drop here. When lock guard is dropped or destructed, then, as we discussed, the underlying lock should be automatically released. How can you do that? We are doing that by calling unlock function using the token. So that's all. We just unlock the thing. And that's the only thing we need to do at the end of the lock guard. Let's see that the implementation here, invocation of unlock, is wrapped with unsafe because, as we discussed, the inner low rocks unlock function is unsafe. It should guarantee that the token should be the same with the one returned from the lock function. But it is guaranteed by our implementation. The token here, self-dot token, is actually one that is returned by the lock function. That's the reason why we satisfy the guarantee or contract that is set by the rollock API. That's the reason why we don't need to mark this function as unsafe. It is always safe to drop a lock guard because the underlying data structure's invariant is guaranteed by ourselves. So you need to see the unmarked wrapper here, and this is precisely the locations where we need to manually inspect whether we satisfy the guarantee or not. Okay, so far so good. And how to use this lock guard? So these two trait implementations are the most important and interesting part of the question. So when you have a lock guard, and then you can dereference the inner data type. Lock guard, as I said, is a guarantee that you have acquired the lock. So you can mutably and immutably access the inner data. That is guaranteed by these two functions. So when you have a lock guard, then you can dereference the inner data. The implementation is, as I said, unsafe because the fact that you can access the inner data is guaranteed by the implementation of a lock. Similarly, you can mutably dereference the inner data. Also, the implementation is unsafe because the invariant that you are the only one that accesses the data is guaranteed by the implementation of the Spinlock, not by the type of Rust. It is not automatically correct. Okay, so far so good. And it has other kinds of APIs which makes our lives easier. And please look at the other code as well when you are inclined to do. And this is basically the APIs of and a little bit implementation details of this Spinlock and higher level API of lock. Okay, so far so good. And so far we discussed many kinds of low-level APIs of concurrency libraries. It is very low level. It is about locks, structs, and conditional variables, etc. And let me show you a tease of a very, very high level of parallelism library API. And this interpolator is the epitome of such an example. Okay, from now on, I don't want to discuss concurrency at all. I just have a range that has 100 elements from 0 to 100, and I will just want to perform an action here in parallel. That is all I want to do, and that is the idea that I want to implement in this code. How? If it were to implement with a low-level API, then we need to somehow synchronize multiple threads and distribute the work into the multiple threads. But it is very much low-level detail. I want the library to deal with that on my own instead of I do it on my own. This line does that. This line automatically parallelizes the job to multiple threads. If your CPU has, for example, 16 threads, then it will distribute the work across 16 threads. It will automatically detect the number of CPUs you have, CPU cores and threads you have, and it will automatically distribute the work to multiple threads. So that's all. And that's the old code that is needed to parallelize your workload. So here is the code that is cut and pasted from the example. When you run it, it is actually doing it in parallel. From here and to here, you cannot see whether it is actually parallelized or not. But here, there is there is missing values that is executed later, right? So this is precisely where this is precisely the evidence that parallelism kicks in. The range from 50 to 74 are executed in a different thread, but they are scheduled later. So that's the reason why they are not executed before 75. So it basically proves that, oh, this code is parallelized and executed in multiple threads without knowing any kinds of low-level details. It is very much high level. It doesn't even mention thread, but it is automatically distributed across multiple threads. The further benefit is that the API is 100% safe. When you use interpolator, you don't need to worry about the correctness of this library. The library author should have already taken into account the safety in their implementation. So this Rayon is, but under the hood, the Rayon is implemented on top of the Crossbeam, which is a heavyweight concurrency library for Rust. And in the next video, we are going to study the Crossbeam and its a few APIs.